participants and okay, very good morning to all the participants and today we have our resource person Professor Somya. She is from DAIT. So I welcome you, madam, for this
Thank you, sir. Thank you, sir.
Session on robotics. And to give a brief introduction about Dr. Somya. Dr. Somya S is an assistant professor at School of Robotics from the Defense Institute of Advanced Technology, Pune, where she leads research in robot dynamics and control, modular and medical robotics, non-linear control, and robot path planning. So our domain is very, very relevant to our topic, that is leveraging the automation or using robotics for Industry 4.0. She received her BTech in Electronics and Communication Engineering from Puducherry University in 2009 and her MTech and PhD degrees in Control Systems and Robotics from NIT K. Surathkal in 2012 and 2012 respectively. Prior to joining DAIT, she served at Manipal Institute of Technology in Manipal and has been invited as a resource person for several faculty development programs. That's how I came to know her by attending one of the online FDPs, and she was one of the coordinators in that this one organized by DAIT itself. She served at MIT and DRDO sponsored workshops. Dr. Somya serves as the principal investigator and co-investigator on multiple DRDO funded projects in humanoid manipulation, distributed control, and UAV based optical communication. At DAIT, she also plays a pivotal role in shaping the MTech curriculum, that is automation and robotics curriculum, fostering academic defense collaboration with labs such as CAIR, then R&D, DEAL, and RCI. A member of IEEE, CSS, RAS, RSI, and across, she has reviewed for reputed journals and conferences, and is a recipient of several honors, including the AICT National Doctoral Fellowship, NDF, then AICT PG Fellowships, and JASCO Scholarship Japan. Her research bridges advanced control theory with real-time robotic systems for defense and strategic applications. Madam, we are really honored to have you here as today's resource person. So she'll be dealing with advanced robotics. Yesterday you had the Marilyn talking about the basics of robotics. So today is the advanced topics on the subject. So kindly make use of the resource person and let it be interactive. And she also research paper article published by the madam will be discussed between 12 to 1, followed by lunch, and post lunch you have again a person from industry, that is Mr. Harsha. He is from Silicon Microsystems. He'll be dealing about automation and robotics. And after that, as you required, you'll have the hands-on sessions. The same. Today we'll go much earlier to the lab, and so that you can have much more practice. Okay. So this is about today's program. So I thank you. I invite Madam Professor Somya to take over. Thank you.
Thank you, sir. Thank you for the nice introduction. This is definitely for the webinar. Okay. Thank you, sir. Thank you for the nice introduction. So, sir was actually sending me the details of participants. So said that, few are from robotics background, those who are working, and mostly from mechanical, electronics, and computer science. Others are from. So may you know who's basically from the robot, uh, you know, platform? I mean, robotics. Anyone? Okay, you are. Uh, you are automation. Okay, okay. M Tech me or you're teaching, sir? M Tech me. Okay, okay. So basically, today my flow of presentation it is going to go in this way that basics on our path planning and what is glitches which we have in path planning and basically how we can address it. So and go through, I means I am a person who is basically working in the control aspects, and you know that how it will be when we go ahead with the control theory. It will be purely mathematics and it will be kind of scratching head at the end of the session. Okay, so that is what is my experience previously. So what I do is I'll go through the contents and I'll convey what is actually the the drawbacks or issues which is there in the path planning and how we addressed it minimally, and I'll give you the paper reference which I have done, and finally we will move on to the paper discussion at 12 o'clock. Okay, so this is what I have planned on. So last sessions you would have been got a very good introduction on robotics, right? So what is mean by robot and the history of robots and how do we classify the robots, right? And how we go ahead with the motion planning, all these concepts. Am I right? Yes. Yeah. So I'm starting from that point, okay, where other professors actually stop. So if you look into this slide, basically you can see here that there are different type of robots over here, right? So what all the robots we have over here? We have kind of manipulator, right? We have kind of manipulator which we can see serial number 7, serial number 3, etc. Then we have, here the drone, which is actually, rotor based. Then we can see some underwater vehicles. We can see some, track path robots. We can see, the ship like, the surface robot, right? So when we look into this kind of robots, we can see that like with reference to the motion, okay, we will be able to do the navigation. It is not like whatever the algorithm which I prepare for, the Jacko manipulator arm, I won't be able to use it for my drone. I won't be able to use the same for my, robot which is actually navigating in the ground or which is actually going through underground, right? I mean underwater, right? So like that, what all the parameters or what all the contents we need to basically change when we think about the navigation of this particular robots. Okay. Now, if I look in from that point of view, I can see that first I classify them, okay, with reference to the motion. Okay, then I move on to the, path planning component of that. Now, I can see here that this robot, basically I'll be able to classify with reference to their motion. Okay, I can classify them under basically two categories, that is nothing but the static robots and the mobile robot. Okay, so coming into this, the static robots are nothing but which we call it as manipulators. Again, we can classify these manipulators into three types, like serial chain, and then parallel chain. Then we can have a hybrid kind of manipulator. Now, coming into the serial chain is actually nothing but, the basic building block of this, manipulators are nothing but links and joints. And especially when we talk about robotics, we will limit our joint. We have different type of joints, right? Joints like it can be parallel, it can be a revolute joint, it can be a prismatic joint, or it can be a universal joint. Like that, we have different kind of joints, out of which we use only two type of joints very widely in robotics. That is nothing but our revolute joint and prismatic joint. The revolute joint is used for the rotary motions and our prismatic joint used for our linear motions. Why we are limiting, the degree of freedom in joints is nothing but to understand or for the easiness in controls. Okay, controlling a single degree of freedom is actually easier and comfortable than controlling the multiple degree of freedom from a single joint. We can, if we need more degree of freedom, basically what we does is nothing but we keep on adding the joints such that we will be able to get the degree of freedom which we want. That's how we process. So this is what is basically about manipulators. Now coming into mobile robots, again we can classify the robots into different category, that is ground, aerial, surface and underwater, right? So in this, especially we are much bothered about, the ground robots, that is nothing but wheeled, tracked and, legged and other kind of, or combinations, hybrid kind of, robots, which can navigate, in the ground. Then again we have aerial vehicles, we have surface and underwater, which is having its own way of designs, and it is having the dimensionality things and the movements and all, it's different. Now if we look only into the ground robot, okay, which we have classified over here as wheeled, tracked, legged and hybrid, how do we navigate them? Is navigation in all this type of robot is actually basically same, or motion planning is same for all these robots? Mobile robot, leg robot, okay? So again, when you come across this classification, we can say that, the path planning or, the motion planning of these robots are actually entirely different. How it is entirely different? Because if it is a mobile platform, we know that there will be a differential drive, it may be attached with the robot, and with reference to, basically it is the revolute joint, right? So with the reference to that, it will give the rotation motion, we will convert that into corresponding linear motion and we will be able to get the distance, right? But if we look into the leg robot, then leg robot itself we have classification, right? Leg robot may have two leg robot. It can be a four leg robot or it can be a six leg robot like a spider, etc. Right? So how do you plan the motion in that? How do you make the robot move from one point to the another point by giving corresponding control signal? Is it is the same? It is going to be the same for all, at least for the leg robots? No, right? Because what the change over here is nothing but, the planning itself, we call it is, the motion planning itself, we call it in different way over here. That is nothing but, if it is a manipulator planning, we call that as a trajectory planning. If it is a mobile robot planning, we call that as a path planning. If it is a leg robot, we call that as a gate planning, right? So now what is the difference between all these things? What is the difference between trajectory planning? What is the difference in path planning? What is it about motion means gate planning for your robot? So the one thing is nothing but, when we consider a manipulator, we have trajectory where we are actually bound to have the timestamps, okay, time dependent. And coming into the path planning of your mobile robot, where we are not bothered about the time, but exactly it is not so. Obviously, at the end, to find out, we need to identify the shortest distance, right? So where we are bothered about time indirectly. Okay, so but otherwise we are bothered only about the start point and goal point. If a robot is able to avoid the obstacle and if it is able to reach the goal point, we can say that the robot is successfully planned its path. Okay, and what is this gate planning now? And coming into the gate planning, is the gate planning easier compared to path planning or trajectory planning, or difficult? it should be difficult, right? So why? Because he is nothing but the, the dynamics of the mechanism and the degree of freedom which we consider over here. Okay, and there is something called as, when you talk about a, leg platform, basically we are bothered about the stability of that mechanism also, right? If you don't actuate any of its joints, associated with the leg or, platform, it will collapse basically, right? So that is what is a major disadvantage again, which is, which we need to look over here. So I have planned in such a way that first I will discuss about few path planning algorithm, then, what we have, what is my contribution in that path planning algorithm, then, slowly moved on to some, simulations which we have done it in using ROS or web platform. Then the paper discussion will be actually on your leg platform, that is nothing but a humanoid platform. Okay, so this is how I have planned the session. Now, as I discussed, you can see here that we have path planning, trajectory planning, and we have our gate planning. So all these three platforms, basically, whether it is a mobile platform or whether it is a, manipulator or it is a, leg platform, the goal is basically same. It need to start from a starting position and it need to go to the goal position by avoiding the obstacle. Okay, it should not hit the obstacle and it should move on, it should identify its own trajectory or path, and it should need to reach the goal position. So, how efficiently we will be able to do this, and this will be purely dependent on the application too. Like, sometimes you need to move, very precisely. Sometimes you need to move very quickly. Okay. Sometimes you need to ensure that, some object which you are handling should not be, like lose a grasp, etc. Right? So depending upon the application to application and the environment. When I talk there about the environment, what would be the change in the environment of this particular, robot space? So it can be like this, like in the sense static environment. When the class is going on, all of you are into your position, you are not moving. All the obstacles or objects over in here in this classroom is basically stable, right? Stable in the sense it is actually not moving, right? So in that case, if I ask a robot to move from one point to another point, it will be easily able to move with the help of a sensors, right? Whereas if it is a break time and nobody is over there in the dais, and you are allowed to move freely, you will be walking randomly, right? So there is no fixed path or something like that, where which we call it as basically dynamic world. Okay, so when the world become or the space become dynamic in nature, the path planning will be little bit more complex compared to the static path planning. Okay, so that is what is the two different, environment again when we talk about. Now, if I look into, the path planning component, there are certain things which we need to basically look into. That is nothing but the first aspect is the sensor selection. Depending upon the sensor, depending upon the application, basically you will be choosing the sensors. And if you look into this kind of sensors, basically I can say that, the first basic sensors which you need over here is nothing but, to identify the position, distance, etc. Right? So for those kind of application, you can see, displacement, angle, distance, all this geometric position identification area, you will be using potentiometer, IMU, accelerometer, etc. for this kind of application. Next comes kinematics or the motion. Okay, so how you will be able to identify the velocity, acceleration, all those components over here. So that you will be getting from your accelerometer, gyro, IMU, etc. kind of sensors. Then you have basically obviously you will be using your robots for some specific application, right? It may need to grab something, or it need to, balance some force, counteract on something, etc., right? So where we will be requiring the force or torque sensor. If you want to grab something, okay, it may be a stone or it may be a glass, right? So your robot should basically have the capability to differentiate between these two, and it need to give the required amount of force to grasp this two, right? So where you will be requiring a force feedback at your end effector. Similar way, if you move your joints, move your manipulator joints, or quadruped, or whichever the robot, you should know that how much force or how much torque, if it is a prismatic joint, how much force, if it is a revolute joint, how much torque you need to apply at that joint to move that, to get the corresponding amount of motion. Okay, so you need to have some feedback from force or from torque. Okay, torque feedback, you have both force sensor and torque sensor, you can use that directly. Otherwise, torque sensor is basically costly and complex in functioning. You can use a current sensor and you can take the feedback, and you can use inverse relations and you can manage it. Okay, so then the next thing is nothing but the very important thing is, perceiving the environment. Okay. So if I need to navigate from the start point to the goal point, I should know that what all there in front of me. And if I am particular about, grasping subject object, I need to identify that object, right? So how I will be able to perceive the environment. Okay. So if I have to perceive the environment, basically again we have lot many sensors available. That is nothing but different type of cameras, lidars. Okay, and then if you are not bothered about the size, shape, and all those kind of the object, then you can go ahead with IR, ultrasonic, etc. kind of sensors. Okay, so then. At certain time, as when we write the control program for our manipulator, means or for your mobile platform, we write in such a way that as the object is coming closer to us, basically we need to reduce the velocity, otherwise it will go and hit, right? So whether you are going to have some near field sensors for that, okay? So in that case, which sensor you will be using, or only you are bothered about only the far distance, object detections. So for that, you can again classify the sensors which you are going to inbuilt in the platform. It can be a near field sensors, or it can be a far field sensors, depending upon your requirement and application. Okay. No, the next point comes is like, okay, we are talking about the sensors. Sensors are going to be one of the integral component when we talk about any robot, right? What are the integral component of a robot? Sensors, actuators, chassis, controllers, right? So these are the four integral component of the robot, and one of the major integral component is nothing but your sensors. With the reference to the sensor, whatever the sensor details we are getting, we are manipulating the things for your actuators for the corresponding motions, right? So we can see here that if there is any error in the sensors, which in detection, okay, that error is basically going to reflect in your control algorithm, because it will compute the control algorithm in strongly, because the sensor feedback has given I am over here, but my sensor is saying that I am over there, right? So then my controller will be calculating the required amount of position details, velocity details, and all according to that, and it will be asking me to move from there to some other position, right? From here to that position, but I am already over there, right? So, it is actually going to give you a correct, incorrect, actuation at your joint. So, what all would be the reason for basically getting a incorrect sensor reading? Okay, so that's what you can see here that basically if we look into the sensor, that sensor maybe I have designed a sensor and I'm claiming that okay, I'm in Mysore, I have designed this particular IMU. When I do the measurements, I'm getting the exact value with the reference to the set values. Okay, set values. Then I'm taking that sensor to some other portion, okay, of India, maybe, a very hot region, okay, that is nothing but I'm going to, Rajasthan kind of place, and I'm using it in the readily under the sun in the, afternoon where temperature is really high. So whatever the reading I got over here, I may not get it over there. Similarly, if I take the same module over there to Kashmir, whatever the reading I am getting over there, it may not be basically same as whatever expected. Okay, there will be some changes. So, similar, you can take a simple camera. That camera we are using it in foggy region. We are using it during the rainy time, or if we are using in the normal time. The camera will start giving you different reading for the same distance. Why? Because it's nothing but the environmental parameter have an effect on the sensor reading. Okay, so what we does is nothing but basically we do calibrate the sensor. Okay, we need to ensure that whatever the reading we are getting, it is basically with the reference to the set value and it is correct. For that, if you go ahead with the industry standard, sensors, we will have a pin which is actually looking after this. That is nothing but for your sensor safety and integrity component. Okay, so we will enable that pin. Then we will get to know that what is the sensor reading. We will be able to do the calibrations. We can go ahead with an online calibration or offline calibration depending upon the sensor specs. Okay, so, this is how we will be overcoming that kind of error. Because I cannot say that whatever the sensor I am using, I use only in Mysore. I won't use it to, when I go to Rajasthan or Kashmir, I am not going to use this. I cannot say like that, right? So whenever I design a platform, that platform should be, universal. Basically, wherever I deploy that platform, it should be in a position to basically work, right? So that is where the calibration component is basically coming into picture. Okay, next comes filtering. Okay, so I said that when I go ahead with this kind of sensors at multiple location in India itself, it may not be giving me the correct readings. Okay, now comes, okay, it is not giving, what to do? We will go for the next option. What is the next option is nothing but, I will be, adding on multiple sensor to basically, get the same details. I will have a camera. Along with the camera, I am going to use an IMU and I am going to, measure the distance, okay, or position, okay. So now I have two, reading, which is actually giving me the position of something, maybe obstacle. Even I can say the same camera itself, okay, one camera, and I can have another component as a lidar or something like that sort of, okay, from which I'll be able to get the details. If I have an obstacle, how far my robot is from that obstacle, okay. Again, one more issue which you are going to face over here is nothing but, the sensor signal which you are getting over here. That means, whatever the rate at which your lidar is giving you the signal, your camera may not be giving you. Okay, camera might be giving you 20 frames per second. Your lidar might be, bit more higher than that sometime, right? So now, how you will match it? Okay, my camera is saying that obstacle is at of 10 centimeter distance, but my lidar is saying that the obstacle is of 15 centimeter distance. Okay, now how you will ensure that what is the distance at which sensor you will consider now? LiDAR. Okay, so he likes LiDAR. Okay, then only LiDAR you will be answering it. So we cannot basically go ahead with a single decision like that. Okay, I like LiDAR, so I'll go ahead with the LiDAR. I like camera, I'll go ahead with the camera. We cannot do like that. That is where this component is actually coming into picture. That is nothing but sensor fusion. Okay, so we have different type of algorithms like UKF, EKF, etc. Okay, extended Kalman, different type of filtering where we will be doing the sensor data fusion, and we will be getting the accurate distance details and things like that. Okay, so like that we will be able to get it. And the another component is nothing but, redundancy. That is nothing but, the same camera itself, I'll place one more. Now, instead of one camera I'm using, I use two cameras of same type and I'll try to get the signal from that. That kind of, platforms are also we have, where if one goes, one gives you the wrong reading, the other one will be the correct reading. That may be helpful, you're initiating the camera calibration details and things like that. Okay. So this is how your, sensor selection is actually, very important for your robotic platform. Now, coming into the control aspect, if we look into the control aspect for your robot platform, you have, different control of, methods which is available. The classic control method, modern control, method, and, AI based different type of, methods. Okay. Now, which kind of control method we will be, choosing for our platform to, for planning the motion? Okay, whether I'm going to choose a modern control or whether I'm going to choose a, classic control, or whether I'm going to use a AI based control or machine learning based control. How do you choose that? It purely depending on your application and the capability of your robot. Okay. So if it is a simple application where it need to move from one position to another position, I'll be choosing a simple Arduino based controller where, I don't have to go for a complex controller. That will be more than sufficient for me. Right? So if I use an Arduino kind of controller, obviously I cannot go ahead with the AI or machine learning based controllers, right? The issue is like it doesn't have, the capability to process AI based components, right? Like machine learning training and all, it won't be able to do it. So then what I can do is like I have an option of my classical and modern control, or I can go ahead with a simple hybrid control method to go ahead with. Okay. And each and every control over here has some advantage and some disadvantage. So when we choose a controller for a specific application, we need to again think on this part too. Okay. And when your control goes, non-functional, okay, in that case, what would be the reason if, I have chosen some right controller and I'm saying that with this parameters, basically, the controller will be functioning very smoothly. In that case also, even after implementing the control method, it is not functioning smoothly. So we can say that whatever the model we have chosen, model we have done, okay, there is an error in model. So that would be the one reason. Then you can see here that, whatever we have modeled on that, an additional disturbance is actually coming into picture, which, the control cannot take over. Okay, that would be the other reason. Otherwise, we said that, we have user sensors. In that sensors, basically some noise is there. Because of that, it is actually not of taking the correct value. Okay. And otherwise, there will be some, we can go ahead with some fault tolerant control. Even if there is some fault issues are there, it will be, tolerated and it will be able to control it. Okay. Or, we can say that unknown dynamics. The dynamics is actually not completely known to us. In that case also, there will be some error. Okay. So, this all are the possible uncertainties which can come into picture when you think about a robot control. Now, we are saying that, if the sensor malfunctions, we know that sensor details are actually wrong, right? And we are saying that we have different method to overcome that. Even then, whatever the details we are getting about, the environment, if it is complete, no. So it cannot be complete and it will be basically partial, whatever the details we are getting. Now we are bound to design a perfect controller with reference to the partial details which we got it from our sensors. Okay. So that is what is one of the challenges we have over here. You can see here that this environment is basically static in nature, and the robot that is why is able to, and it is more than that, it is an indoor environment, right? So it is able to pick from one place and it is actually able to place it in another place. So now we can say that there are so many limitations are there over here. That is nothing but the knowledge representation about the environment. Then we have different uncertainty in the world. That is nothing but from environmental point of view, the climatic point of view, terrain point of view. Like that, there are different kind of uncertainties are there in place. Then we have processing limit. Sometime we will be saying that I have to measure a 0.001 accuracy radians per second measurement I need for some of my optical application. Now, if I have to measure 0.001 radian per second, I mean from encoder, I need to have minimum of 32-bit encoder for that. So what is the challenge over here? We don't have a readily available 32-bit encoder in place. Okay. Either we need to modify the encoder which is available, otherwise, we will be losing the details. This we can make. It is whether it is an incremental encoder or absolute encoder, we can make somehow. We can attach more number of digits, or we can code the absolute encoder in a better way, and we can make the signal. But again, the big communication we need to do. There is something called as physical resolution and digital resolution. Until and unless the physical resolution matches the digital resolution, the data transferring won't be happening properly, right? So we need to ensure that whatever the physical resolution we are getting from your sensor data, we need to have the corresponding digital resolution to transmit that. Okay. So if that happens, we can say that our sensor details are basically getting transmitted properly to the controller, right? So like that. Okay. The processing, okay, from sensor point of view. And the other processing limit from your control point of view is nothing but whether the processor inbuilt in the controller is capable to do the calculation. As I said, like we can do a controller, we can implement a control algorithm using an Arduino board or using a NVIDIA board, right? So NVIDIA Orion is one of the good control platform which we generally use it. And we have, Arduino controllers also, which, is inbuilt in the robots. Okay. So, if we want to do some sort of, image processing components in online, then we need to go ahead with, or we have to implement an AI component, then we have to go ahead with your NVIDIA kind of board. Otherwise, it is going to become very difficult for us to, do that process, right? So that is where, the processing limit basically coming into picture from control point of view. Now, yeah, dynamics. So if you take any robot, okay, you can consider your mobile robot itself. The robot is attached with a manipulator platform. Now, the application of the robot is nothing but it need to move a part from one position to another position. So now we know that, if I apply this much torque to each and every joint, the robot will be moving with this velocity, and within this time it will be reaching this particular goal point. Okay. Now what happens is nothing but the robot is actually picking that part, and that part is on that particular robot. What happens over here is like the mass is basically getting increased over here, right? The weight of the robot is basically getting increased. So whatever the actuation you are applying, thinking that this velocity it will be moving in open loop condition, it won't be able to move to that destination point with that particular velocity because of an added weight. Suppose if you have a feedback over here, okay, to understand that the velocity is not matching with the velocity, then what we can do is like obviously we will increase the torque limit and it will move on, right? So there is a dynamic imbalance is actually coming over there when we consider this kind of applications. Then yeah, if we go ahead with the learning kind of method, if we do some sort of all we can see here that overfitting kind of components, then again it is actually going to malfunction. So this all are the issues which we generally face with the control, okay, when we think about the control application. So we can say that perfection is not in basically getting the complete knowledge. It is actually a continual adaptation to your bounded rationality. So whenever we say about any control method, we say that we can classify the control into different type, right? CISO, MIMO, VIVO, etc. Right? The single input, single output system, multi-input, multi-output system. Similarly, we have VIVO system, that is nothing but bounded input, bounded output system. So we can say that if I design a robot and if it is functioning very fine in Mysore, I can say that at this region, that means with this temperature condition, with this pressure condition, and this kind of environment, this gives you, a perfect path plan. Okay, but if this condition get violated, then I cannot promise my, stability of my controller. This is what I will say that bounded input, bounded output control. Now, if I look into the path planning, path planning component, you can see here that the geometry of the environment, the kinematics of the robot, the initial and the goal configurations are going to play the major role. Okay. So the path planner basically compute a feasible and collision-free path to the goal, and finally it will be able to reach the goal point. You can see here that there is a mobile platform. The two green dots over here is nothing but the start point and the goal point, and the green line in between is nothing but the path it is being actually identified, and the orange color which is over there is nothing but basically the obstacles, and the white space around it is nothing but the free space. So this is what we call it as the configuration space of your robot. It is actually a combination of free space, obstacle space, and your goal positions or start position. Okay. And similarly, you can see here that a trajectory planning robot, a manipulator, and there is an obstacle in between, and how it is actually replanning the path from start position to the goal position to reach the goal position. Okay, this is again the same example of the workspace. We can say that free space, obstacle space, and the start and goal position. Now, if we look into the path planning algorithm, we have different type of path planning algorithm, and especially in Chaucer, if you refer, it starts from bug zero algorithm onwards, right? So simple bug algorithm, what it says is like we have a robot, which we considering as a point mass, and in that point mass, basically a touch kind of sensor is basically attached on it. Okay, so once the robot go and hit an obstacle, basically it sends that there is an obstacle, and we can program in such a way that if once it hit the obstacle, it can take a left turn or a right turn depending upon the algorithm. So once it take the left turn or right turn, again what it does is like it will circumnavigate that obstacle. So which is actually wastage of time. It doesn't have to do that, right? Then it will be moving on. It will be identifying the best path from where it can actually jump to the goal. Okay. So that is what is this is the obstacle, starting point and goal point. This is obstacle. And it will be, coming, hitting, and it will be circumnavigating. Then it will identify the best point. From that best point, it will be again moving on, try to move on to the goal point. Here, again, when we talk about path planning, we can, talk about the path of a robot from two perspectives. Okay, that is nothing but, okay, yeah. So whether it need to basically map the environment and need to do the path planning, or that environment is known to you. Okay, if the environment is known to you, you know that where is a goal position and where is the start position. Obviously, you will be able to reach to the goal position without any delay, right? We have so many equations associated with it, like in Manhattan or Euclidean distance formulations. Using that, we will be able to identify the XY locations, and we will be able to calculate the shortest path to that. Now, if you don't know the environment, what you does is nothing but you will do the mapping, then you will do the path planning simultaneously or after that, right? So this is how we will identify the goal position. Now, you can see here that in all these bug algorithms, we assume that the start point and the goal point is actually known to us. In that case, the initial bug algorithm says that it need to circumnavigate, then it need to identify the best point from which it can jump, and it can move towards the goal position. And then, series of bugs are there. Bug 0, bug 1, bug 2, and tangent bug. So what happens over here in the updated version is nothing but they have come up with something called as Manhattan, the straight line, M line. So the M line is nothing but, the shortest distance from the start position to the goal position. It will draw a line from start position to the goal position, an imaginary line, which is nothing but the shortest position, right? So we calculate all the x, y, z for that. And once it hit the obstacle, it will try to identify that, closest point from there. Then from there, it will be jumping on to the next point. So this is what is update. Then the next part. Then when it comes to tangent bug, what it does is nothing but instead of a touch sensor, basically it is having a sensor which have a field of view. Okay, maybe a camera or some other kind of sensors. Okay, so it will be able to identify the presence of the obstacle in prior, and it will be able to avoid the obstacle. So this is the initial algorithm which is actually which was initially in place. It's algorithm used all types of mobile robots. No. I'll come to leg robot. As I said to you, the planning, motion planning for leg robot is entirely different. In the sense, it will be, that we call it as gate planning. We won't call that as a path planning. It is a gate planning. Yeah, where in, leg platform, we basically consider the dynamics. We consider the path which we want to move on. And, we consider the external disturbance. There are capture point we need to identify. We need to identify the ZMB, okay, zero movement point, all those things. It is bit complex than your path planning algorithms. Okay, that paper which we are going to discuss on is same. Okay, we are going to discuss on the humanoid lower body. So there we will discuss on this. Hmm? This is purely for the wheel platforms. Okay. So the start point generally we will mention using as Q start, and the goal position will be Q goal, and it will be a mass, point mass, and it will be attached with a touch sensor. And once it touches only, it will identify that there is some obstacle, and yeah. So basically, the small r is nothing but the dimension of the robot. And we can say that, when we talk about an obstacle avoidance, there is one component called as growing obstacle. Okay, that is nothing but the dimension of the robot will be added on to the dimension of the object, such that, we will be able to ensure, the robot will be able to navigate through that path which is actually it is identified. If we are not considering the dimension of the robot, then we won't be able to, sometimes we won't be able to move through the shortest path it is actually identifying. Okay? Right. So this is what is about your one algorithm. It will circumnavigate, then it will come back to the same position. It says that okay, this is what is the shortest position to the goal position, and it will be moving on to the goal position. Okay, so you can see here that that Q1L is nothing but the leaving point, and H will be there. Q2H or Q1H is nothing but we call it as hit point, where it is actually basically getting hit. Okay. Now, if we, always we are bothered about, the distance traveled by the robot, right? And especially when it is an autonomous robot, the battery backup for that robot will be lesser. We have some limitations. We cannot go ahead with a tethered mobile sometimes, right? For example, search or exploration kind of, applications. We won't be able to give the tethered supply to the robot. It will be a fixed, battery platform which it has. With that, it is supposed to navigate. So in that case, we will be very much bothered about the path the robot will be actually moving in, right? So, we need to look into, what would be the distance it is actually covering. You can see here that O1 and O2 is nothing but the obstacles which we have in that space. To cover O1, the algorithm is taking the time from 0 to approximately 6. Right? Similar way to cover O2, it is taking from 7 to 10. So this is how we mentioned the, graphically we mentioned the distance it is being covered. Means, used to follow this obstacles. Now you would have gone through the A star last class, right? So I would have been explained represents. So we have again bug algorithm, Dijkstra algorithm, A star, D star, RRT, PRM, like that. N number of algorithms we have, Verneuil configurations. Okay, there are different kind of algorithms, BFS, DFS, etc. Right? So now coming into this A star algorithm, how we do is nothing but we can say that the function will be equal to g of n plus h of n, where g of n is nothing but the cost at which the path is actually discovered, and h of n is nothing but the heuristic function over here, right? So what is meant by this heuristic function is nothing but if I am into a point, I have an option to move forward, backward, left, or right, right? So I need to choose among all these options. Again, in A star, we can go ahead with a 4-point decision or 8-point decision. If it is an 8-point, the 8 circles, I mean 8, column or blocks around one column, I'll be able to, plan. 4-point means I will be considering only forward, backward, left or right. Okay. So we can say that if it is an obstacle is filled, it will be of high cost such that it won't be considering that particular column. And if it is diagonally moving, it will be 1 by root 2, that is nothing but 1.4 will be the cost. If it is forward, backward or left or right, it will be basically costing 1 unit, right? So according to that, you will be adding g of n plus h of n and you will identify which is the lowest one, then you prefer that such that the cost computation will be lesser to move from the start position to the goal position. Okay. Yeah. So this is one of the example which is actually shown. And basically, we will consider even the Manhattan kind of, your Euclidean kind of distance also here. Then comes RRT, that is nothing but rapidly exploring random trees. Okay. Here, what happens is like we have an area and I want to quickly identify the goal position over here. Okay. How can I move from the start position to the goal position very quickly? For that, what I'm going to do is nothing but I'm going to sample this particular area. Okay, I will identify some random 100 points. I can sample 1000 points. Okay, it's up to me how many points I have to sample. So first I will sample. I'll say that randomly I am generating some 100 points in this area. Then I'll have my start node. From start node, I'll see that which node is closer to me. I'll move on to that. Then from that point, I'll identify which is the next, nearest node for me. I'll jump into that. Like that, by keep on counting the nearest node size, I'll be able to reach the goal position with the minimal cost. That is what is the concept which RRT is actually talking about. Okay. So this is how I will be able to quickly reach to the goal position. Yeah, you can see here that there was a near point. Near point is nothing but the initial point, and it is actually identifying the near point. Then, from near point, you will be identifying the new point. That is nothing but you have n number of samples in that space or nodes in that space. So, which is the nearest one, you will be jumping onto that, or you will be making a path with reference to that. Okay. So this is what is the algorithm related to RRT. Like, initial, then you will be basically through iteration, iteration, you will be generating n number of points, random points. Okay. Then that random points, you will be actually assigning, you will be considering to move on. You will be identifying the shortest distance, point or node from that. Then you will be jumping on to that. So this will keep on continuing and you will be able to reach the goal position. Okay. So now, if you ask me, like, we have so many algorithms over here, RRT, starting from bug, A star, RRT, etc., A star, D star. So many algorithms are here. What we have done over here is nothing but a simple work where, the robot, I have fixed an environment. Now I wanted to know that in that environment, which robot actually perform better. Okay. So for that, I have actually implemented some 3-4 algorithms in that static environment, and I have analyzed the cost, and I have identified that for that particular environment, which robot is basically functioning better. So RRT, I have RRT, PRM, A-star, and digital algorithm I have implemented. And the path length I have identified from that. Okay. Then the execution time. Then the total cost is nothing but execution time into the path length. Then the efficiency. The maximum how much it is taking on that this particular algorithm how much efficient it is. So that has been done. It's a very simple work which has been done as a mini project of one of our MTech student. Okay. So we have compared all those components and analyzed it, and for that particular environment we have identified that PRM is the algorithm which is actually giving us a better result. Now the population is like we are saying that we have actually gone through the shortest distance path, and this might be the cost to cover this particular area. Okay, but what happened is sometimes is nothing but we can see here that this is an environment which we have created using a web kind of platform. Okay, on the left side, you get a ramp kind of thing you can see where the robot will be able to slide and it can move over that. Okay, sometimes our goal point can be of that, or sometimes for the shortest path we will be able to navigate. But if we use any of the generalized algorithm over here, this kind of path it won't be able to identify it. Okay, it will be considering that environment as a obstacle space. It will be basically considering the space as a obstacle space, and it will be avoiding that area. It won't be considering it as a free space to navigate. It will be an obstacle. So now what I want is nothing but I want my robot to basically navigate through that to identify my goal or for my path planning. Okay. So how I will be able to do that? Is it is possible, or I need to consider that as an obstacle only? I want to move through this particular RAM. You can see here that there are so many structures, okay, through which my robot will may be able to, with the reference to the configuration of the robot, it may be able to, move through this kind of platforms. But the sensors which is attached with my robot, it is actually saying that it is a obstacle right now, right? Because previous path planning algorithms which we have looked into, that is nothing but our bug algorithm, A-star algorithm or RRT, basically it will be considering it as an obstacle. Now, sometimes I may have to identify a shortest distance to my goal position. If I navigate through this particular ramp, I will be reaching it fast instead of circumnavigating and all. Sometimes my goal may be located in this, above this ramp. That means there is a plain space over there, right? So I need to navigate to that point. Is it is possible? Above. It is wheeled. You can answer that as it is a wheeled platform. Okay, how do you go then? Yes. Okay, all even if it is a pillar, basically, LIDAR will be giving you the details. Then how do you plan? Yes. So here the angle basically plays major role. We need to identify the angle at which the slope is there. Okay. If we can identify the angle at which it is, this particular obstacle is slanted, we will be able to, identify that whether it is actually able to navigate through that obstacle or not able to do that. Okay, so that is what we have done. So you can see this. It was built about the simulation basically. Only for environment, we didn't bring any robot over here. So you can see here that most of the obstacle or objects are of navigatable, and you will be able to navigate the robot, or you will be able to plan the motion of the robot above this. Okay. Now, how we have planned this path is nothing but you can see the comparison over here. You can see some red dotted line, means red dotted line, or you can see the green line, and you can see the yellow line. So this are all, using the same algorithm we have actually mapped to. And you can see, if you navigate through, you can see there is one green point with a, red point dot, right? That means the robot is actually navigating through that particular block, okay? And you can see downside also there is a green point, that is your goal point, and this green point is nothing but your start point. So sometimes if you navigate through this, obstacle which is navigatable, you will be able to reach the goal faster. Sometimes your goals will be on top of that. Okay. So how we have done it, nothing but you can see here that the same A-star algorithm we have used over here. And we have two components which we brought into, that is nothing but the vertical and horizontal distance. And that is NV and CNH and CNV. Okay. And you can see here that we are looking into the tan angle. If we identify the slant of that obstacle, slant angle of that obstacle, we will be able to identify that with the configuration of the robot which we have, whether we will be able to navigate through that obstacle or we won't be able to navigate through obstacle. Okay. So that is how it is being done, and you can see here that the total cost for covering the red line, yellow line, and green line. Okay, how much it is?
Total cost is what?
Cost is nothing but the time taken to travel and the length of the path, basically from start point to the goal point. So that is what is actually contributing towards the cost of that particular path. Yeah, length and time. We are considering only the length and time. Okay. So now the second case is like, okay, we are saying that first initially it was like obstacle was identified as an obstacle, and we were doing the path planning. And the second case, what we have done is nothing but we are identifying the robot object or obstacles where we will be able to navigate through, right? If it is a navigatable, ramp kind of structure or something like that, sort of, then you can navigate on that and you will be able to reach the goal position. Now, the next component is nothing but suppose, we have a dynamic, way of environment. Generally, we talk about a static environment. Now, if we have a dynamic environment, if I implement, A star, D star, RRT, or, any of this algorithm, whether they will be able to reach the goal point. Okay. So, or how it will be basically behaving, whether it will reach the goal point or it will stuck as it is. Okay. So that is before that we have done again one more basic simulation. Okay. Yeah, actually, so all these humans will be actually moving in this environment, and how the robot will be basically moving from one point to another point. Now, if you look into whatever the simulation I have shown, you can see that there is some algorithm is there. There is one robot inbuilt with some sensors, actuators, and all those things are there. Okay, and you are able to finally visualize the start point to the goal point and how it is basically navigating, right? So, how you will do this kind of simulations? What are the possible, ways to do this kind of simulations? Is it possible or not possible? Okay, then how? Is there any single platform or multiple platform? Multiple platform. Which are the platforms? ROS to Gazebo, Rewards. Yeah. So basically, if we look into it, we have to work on some, algorithm. At the same point of time, if you want to see the animation and if you want to, implement a very good control law, the number of platforms available are actually very few. Okay. One, I can say that MATLAB. MATLAB has an inbuilt functionality for control algorithm. It has, animation component which we can simulate, and we will be able to come up with our own algorithms to implement that. Okay. Now similarly, if you want to go ahead with a little bit more on the distributedness and all when it comes to the robotics, you can go ahead with ROS 2 is available now. So ROS can be integrated with multiple platforms like ROS MATLAB will be one combo, or ROS rewards we can do it, or ROS with Gazebo we can do it. Okay, like that, we can write our path planning algorithm and control algorithm using a C software or Python libraries, and we can implement for visualization the Zero kind of platform, and we will be able to visualize our path planning algorithms like that. Then Weboards is another platform. Yeah, there are not many differences in this. Okay, so you can say that if I am using MATLAB, MATLAB is actually inbuilt with so many libraries, as you know, right? So MATLAB would be one of the very good platform if you want to write an easy control program. Okay, you have Simulink inbuilt in, you have workspace. You can just in Simulink you can just drag and drop the the components, and you will be able to and you can design any of your control algorithm over there with very easiness. Within no time you will be able to do it. And coming into ROS, basically, ROS may you will need to know very thorough programming. You should be very good in Python or you should be very good in C. Okay. Without that, you won't be able to write the programs in ROS. Once you write that program, you need to know that how to bring all these components together. That is nothing but how to integrate your control program, trajectory program, or trajectory or path planning program. You will have something called as URDF. Okay, that is Universal Robot Description File. Okay, that is actually giving your world plus your robot, that visualization component. That one. Okay, all these things you will be integrating together and you will be launching it using a dot launch file over there. Okay, so you should have a very good understanding in the Linux platform too. Then if you are comfortable with all these components, you can go ahead with ROS. Okay. Otherwise, you are not comfortable with Linux and this kind of basic programs, then you can go ahead with MATLAB or Weboards. One of the advantages with Weboards is nothing but the sceneries are actually readily available, or it is very easy to create from the existing models. Okay. Suppose if you consider a component, I said that it will be humid, it may be raining, it may be snowy. Snow itself, we have, I can classify that into three categories. That is nothing but soft snow, which I'll be able to, throw. And there is something called as medium level snow, which will be little harder than the soft snow. And there is something called as hard snow, that is nothing but our ice cube kind of, thing. So all these things we can say it has actually, three levels of snow. So if we, especially when it comes to robotics, and especially platforms. If you are going to work on the leg platform, there is one more, when you do the gate planning, there is one component which is going to come into picture. It's nothing but the reaction force from the ground. Okay. So that reaction force for these three components will be basically three different values. Okay. If it is a soft snow, it will be basically piercing into that and the reaction force will be lesser. If it is a medium snow, it will be medium hard and the reaction force will be of some amount. If it is a hard snow, it will be equivalent to our hard terrain and the reaction force will be something different. Okay, so your robot should be, capable to understand all these things also with reference to the feedback values from the sensors and environment and things like that. So this is what is one of the again challenging problem when we talk about robotic, motion planning with the like platforms. Okay, like that. So you can use any of these platforms, and this kind of environment you will be able to bring it in using robots easily compared to placebo. Okay.
Actually, in offline for planning, so whether sensors are necessary for a robot.
Sir, offline path planning also, what we test is nothing but it is not computing the, the path with reference to the, the environment which we have right away. But to ensure that the predefined path the robot is navigating, obviously you should have a closed loop control. Otherwise, how do you ensure that, the robot is actually moving in the desired path, given path? To ensure that you should have minimal set of sensors. It is like I can say that the number of sensors which we use it for online and offline computations will be different. So as we discussed, ROS is one of the very good platform where we can do this kind of simulations. Okay, and when we talk about ROS, we have nodes and we have publishers and subscribers. If we, the sensors and actuators are there and controller also, whatever the sensor readings we are getting from, the robot, it will be published to the controller, and the controller will be subscribing that value and computing that controller component, and after computation again it will be publishing through a node to the actuators, and actuators will subscribe that and it will be giving you the corresponding motion. Okay, so that is how ROS work, and the advantage of ROS is nothing but compared to the other platform like MATLAB, Remotes and all, it will be basically centralized computational facility. In ROS 2, in ROS 1 basically if you talk again, master and slave component was there. Master and you have multiple slaves. But ROS 2 is completely a distributed system if you want to work, especially the swarm kind of thing experiments if you want to do, this will be the one of the best platform. Yeah, so if we closely look into the ROS platform, you can see, these are all the specific folders which we have inside. You will be basically having one project, and a project there will be a workspace. In workspace, you will have multiple, files like build, install, log, and SRC. Again, under SRC, you will be having all the files related to your robot. Okay, you can have package, source, setup, all the things, your control program, your launch files, everything will be there inside this particular SRC. And yeah, this is what is a bug zero algorithm in ROS. So how to simulate, because I cannot, it is done in a workstation, I cannot bring that over here. And that's why we have taken a screen recordings of that. So you can see here that, first we will go to the, ROS file. Then we will go to the corresponding file using the cd commands. Then we have a launch file which is actually already written over there. So once we launch that file, our program will initiate and it will be basically functioning as required. So ROS, you can use it using either using an RMS kind of platform which is readily available, You know what is the difference between RVs and gazebo?
Just a simulation. Everybody is just simulation. And artificial we can particularly map the environment. We can see the environment. What is the robot is capturing, mapping.
Okay. So actually this mapping, what the robot is mapping, we will be able to see through any of this platform. It can be RVs or gazebo. The major difference between gazebo and RVs is nothing but RVs is not a physics engine enabled, platform, whereas gazebo is a physics engine enabled, platform. And most of the cases, for example, if you use an RVs and if the robot basically hit an obstacle, or I can say that if it is an RVs platform, the robot will be, moving through the obstacles because there is no physics, it is not sensing that it is an obstacle. Okay. Whereas if it is a gazebo platform, it will be identifying that it is an obstacle and when it hits, actually, what is the impact it is coming into picture. All those things you will be able to analyze using gazebo platform. So the file is launched now for bug zero algorithm. And you can see here that this is the webboard platform. Okay. And you can see there is a GC Tronics robot over there. Okay. And the robot is actually now started moving from start position and it need to go to some of the goal position. Okay.
What language you have used?
And we have used both Python and C. We can actually, webboards, we will be able to use multiple language. Either we can use Python codes, we can use C programming, we can use MATLAB programming, also we can use it in webboards. Any of this language you will be able to use. It basically support up to 5 languages. You have type Java, .NET and all also it will be supporting.
You want to learn.
Python will be basically little easier because it will be, like the language which we use is actually similar to. No. In software there is no difference basically. If you want to learn Python and C, user friendly is Python basically. Yeah, you can see here that now the robot is actually navigated to the goal position. Okay. So this is being done using both ROS and Webboard based platform. The environment which you are seeing is actually in Webboard, and whatever the programming we have done is actually in raw through ROS. Okay. Basically, all the details of the sensor details of the robot is getting published from Webboards to ROS, and ROS is subscribing all the details and it is computing the control algorithm and it is publishing the control input to the webboard. So webboard platform is subscribing all those components and actually it is moving. Okay. Now this is an A star algorithm in ROS. It is in ROS too. Webboards and ROS both are actually open source platforms. You will be able to download and use it. And MATLAB is actually subscription based. So basically for any kind of, simulations, we either use ROS or webboards. If we have some, very complex environment where we need to create or we need to navigate the robot, we use webboards. Webot ROS combination or only Webot? So you can see here that, so this is what is the shortest path actually it is navigating through using our A star algorithm. Okay. Now if we have to simulate RRT in ROS, you can see. So the advantage, if you want to start with learning these things, already these files are available in GitHub. Okay, I'll be able to share the file details of the GitHub. You can download it and you can just run and see, visualize. And you will find lot many other, resources also, similarly. So the problem over here is like you need to go to that particular folder to, launch it. That takes, that integration. Either you need to create a launch file or you need to initialize it one after another. That's where you can see some 3-4 platforms, now because we didn't prepare any launch file over there. We are launching it from, different terminals one by one. Yeah, we have a turtle boat over there in our lab. So we have implemented the lab, and we have seen like the performance level also. There will be a delta change basically. There is there. In fact, we have done one simulation in this way. We have, Blender software. Blender is basically an animation software. We have used the Blender. We have, designed a robot that is animation software, right? So then that animated component we have switched to, the simulation based platform where the physics engine is available. Okay. Then that physics engine available thing, we have actually 3D printed it, basically that model. Then whatever the control we have given to the physics engine based robot, we have given to the real time controller. It was showing some lag in the, but not much. A small delta change is there between all three. So here inputs are actually given through the window, okay, an online window. Huh? I know some places actually already existing models we have used. For example, if you go to Webots, you will get almost all kind of platforms over there, like whichever is required for you. You will be able to, if you are ready to use the Webots, you can use it over there itself. Otherwise, you can export that file as a URDF. Entire scenario, you can export it as a URDF. You can launch it using ROS through your RVs or your Gazebo platform. Then you will be able to navigate over there. You don't have to mandatorily design all the time. You can use the existing, if your purpose is not to, design a robot, you don't have to do that. If you are, you need to understand path planning or control issues, then you can use available platforms. Yeah. So you can see that whatever the goal position given over here, it is being raised the target. Okay. So this is what is the Robot platform, which is actually free to download for everybody. Like you can, Robotics website, so you will be able to download it. Now we can see here that this is another, yeah, how to integrate between. I said that I can use either ROS Gazebo, ROS Arvis, or ROS Robots. I will be able to use it, right? So it is not that easy as we say that integration. So there are some procedures or set steps are available to integrate. So how we can integrate is nothing but this is what is a Robot platform. When you start Robot, you will be getting a tiled platform like this, and you will be you can see on the left side you will be having dropouts like word file, etc. So you can see here that the last option is nothing but a rectangle frame, right? Rectangle arena, right? So if you enlarge that particular portion, under that you will get multiple sliding components through which you will be able to adjust the dimension of the arena. Okay. So once you adjust the dimension of the arena, you will be able to modify the arena components. You will be able to add the obstacle, as you wish. If you want to add some ball, some rock, some, barrel, whatever you want to do, or if you want to, change that into some different environment. We talk about indoor and outdoor, right? So all those components are actually available inbuilt in that. You will be able to either drag and drop it or use it from the another simulation, and you can make your own world. Once you make your own world, there is a slide component which is available on the file. If you click on the file, you will get one more option like new component. Go to the new component, then you will be able to get different type of robots like all the standards robots, manipulators, or your leg platforms or wheel platforms, etc. And you will be able to basically use them, bring them into this particular arena, and you can you can open a new control program over there, and you can write a new control program specific to that particular mobile platform. When you run, you will be able to run the animations in the background, and you will be able to get all the details like position, velocity, everything you will be, even the camera images, everything you will be able to get it from this. Okay. So, and now, so what we have discussed is about, the mobile platform. Okay, so we will have a tea break now. After that, we will resume. Atlas Robot. This is Atlas Robot, Boston Dynamics. Okay. So meanwhile, what I will do is like, I will share a paper in the group. Okay, and I request you to, all of you to go through that. And this component is actually for that particular paper. Okay, so then we will start our discussion. Okay, group. Yes. Yes. Ah, yes, the same. Yes, yes. Mm.
You'll be getting all the PPTs.
Yeah, we can go for a tea break, then we can resume the session.
Boston and so but actually robots company okay. Attuale operatore okay, sir, no problem. Okay. Thank you.
Shall we start or shall we wait? We can start. Okay. Yeah. So actually, what we were discussing so far is like nothing but the path planning algorithms for our mobile platforms. And we said that the similar kind of algorithms we will be able to use it for our trajectory planning also. In trajectory planning, it will be time bounded. In path planning, it is not time bounded. That is the only difference, right? Now, if we look into the other category of the robot which can navigate in ground, okay, or in ground is nothing but leg platforms. And we said that if it is a fixed platform, that is nothing but manipulator, we call it as a trajectory planning. If it is a mobile platform, that means wheeled robots if we use, that is nothing but, path planning. And if we go ahead with, leg platform, it is nothing but gate planning. Okay. So if you are a robotics person and if you would have gone through the, Boston Dynamics website, you will be able to see the robots which is dancing, which is jumping, which is running, which is doing a lot of, things, right? So, Boston Dynamics Spot Robot is a quadruped basically, which is having four legs and it will be able to navigate through the different kind of terrain. And you can see the other one over here, that is nothing but, the Atlas robot, okay, which is nothing but a bipod. When you talk about a robot with a common person, basically what they think is nothing but robot is nothing but which is actually something which is like a human or okay, that is nothing but the humanoid, right? So the difficult part in humanoid is nothing but the controlling, right? How do you control the robot to do some, for some specific applications? The first of all, to ensure that the robot is, able to stand, that itself is a complex process. Okay, so a lot of things you need to, review on when you go ahead with, to make a robot to stand, basically. So you can see here the Atlas robot, it is actually running in a ground, right? So you know the how complex control algorithm and sensors are actually inbuilt in this. Now, what I'm going to do is nothing but a simple gate planning algorithm, which we have done. It is not that simple as I say. You will so far whatever we have discussed is from on the top view of what we have done. There is no complex equations, there is no complex control algorithms which we have discussed. How it is happening only I have said you, right? Now we are going to we are going to dive into the control aspect of this, okay? Only if I consider the lower bottom of this particular humanoid, okay? Lower bottom in the sense only from hip to the, foot, okay? The complexity basically coming into humanoid from degree of freedom basics. Okay, how many degree of freedom you need to control and what need to control for what. That is what is actually creating one of the complexity. Okay, so if I have to plan, game plan for this particular humanoid robot, what I need to do is nothing but I need to give the corresponding actuation at each and every joint of this particular leg, right? And the upper portion of above the hip level, whatever I have, I will be considering that as a point mass, okay, to control or to do this particular gait analysis. I'm assuming that the upper portion weight, how much ever it is coming, the reaction force plus the mass of that particular body, I'm considering it as a point mass, and that mass I'm giving it to the, hip region. Okay. Then I'm going to plan for the gait. Now I want my robot to basically walk. I'm simplifying the problem such that it will be easy for me to go ahead with the gait analysis. Okay. So now what I suggest is nothing but I want all of you to, go through the paper which is actually given in the group. Day 3 paper it will be mentioned as, okay. Yeah, okay. So you can see here that the paper title is nothing but Disturbance Estimation Based Robot Center of Mass Tracking Control of Humanoid Robot. Okay, I'll give you another some 20 minutes would be sufficient for you to go through the paper. So all of you need to go through that paper, okay, and you need to identify the learning objectives, PO, COs, and all. You might be knowing about CO, PO, and all, right? What is CO? Course objectives. And what is PO? Program objectives. So we have this specific COs, POs, LOs. LO, what is LO? Learning objectives. Okay, so you can go through the paper and you can basically identify the this components from the paper. Okay, and the technicality behind the paper we will discuss after some time. Okay, once you complete reading, let me know. Then we will start discussion. Okay. Did you go through the paper completely? Okay. Good. So what did you understand from that? That is what is reflecting over here.
About stability.
Space stability.
Yeah.
Sir?
Suppose that you have basic trajectory.
Yes, sir. Center of no. Yes, 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 yes. Yeah. Anyone else? What did you understand? Balancing with reference to the mass.
UD plus one state feedback controllers.
Okay.
Both together performances.
Okay. Okay. So, when we start from a simple spring mass damper system in our mechanical, we know how to write the equation, right? So, if you want to, analyze the performance of the system, what we test is nothing but first we will design the system. Okay, even if it is a simple spring mass damper system, we will write the equation that is nothing but mx double dot plus, cx dot plus, cx, right? Similarly, so, similar way for any system to analyze the stability component, we need to design the system first, right? Or model the system first. Once we mathematically frame the model of the system, then what we does is nothing but we will put it in a simulation environment. Then we check that whatever the system we have modeled, it is actually stable or not. If it is actually, we can classify the system into basically two types, linear and non-linear. And if we look into the physical system which we have around us, it is nothing but non-linear in nature by default, right? So either we will linearize that system to control it, or we will implement some non-linear control method to, control that, right? So coming into this, we can clearly see that it is a non-linear system. Now the second component coming into picture is nothing but how can I design the system? I said that I am concentrating only on the lower portion of the system, right? So if I consider the human lower body, how do I design that? How many degree of freedom we will have? So in single leg, you can say that maximum of 6 to 6 degrees we can have. Okay. Hip, this like on the hip, which portion which is attached to the hip, 2 degree of freedom. Then knee portion, it will be 1 degree of freedom. Then lower foot region, maybe 2 to 3 degree of freedom, right? So single leg will have 6 degree of freedom. Similar way, another leg has another 6 degree of freedom, right? Now, if I have this kind of system, how do I plan my gait? Now we know that we have two legs, and one leg will be on the ground, another leg we will lift and keep it in front, right? That time this is the system should not collapse. That means it should not fail in movement, right? So how do we move forward? What we can do is nothing but we need to ensure that even if I lift one of my leg, okay, it will be actually stable. And the second component is nothing but when I lift and try to keep my foot on the front side or on the back side, it should not create any instability, right? So how do I ensure that I am not going through that instability? How do I ensure that if I lift my leg and if I keep it on the front side or back side, I'm not coming out of that stability which I have when two hooves are there on the ground? Yeah. So that is where the center of mass component basically play a role. Okay. We need to ensure that the center of mass is actually we have taken care. And if I move the leg forward or backward and keep it, it is not going to collapse. Okay. Now, when I do it, park plan, okay, I can put my leg, when I stand like this, okay, I can put my leg over here also, I can put it over there also, right? So if I put my leg over there, after this tires, what happens? I will fall down, right, by default. So I need to ensure that wherever I am keeping my leg, okay, that position support, my stability. That is where, the center of mass and support vector polygon coming into picture. What we does is like when we are in the ground, okay, this heap portion I am converting it into a point mass I said you. And if I go ahead with the exact system model analysis, I need to go ahead with a 12 degree of freedom control, okay, directly. And sometime, it will be very complex. Not sometime, it is going to become very complex for me to control for gate, right? So what I have done an easy way, which I have identified from the literature, not me, it means the group. Okay, that is nothing but LITM model. What is LITM? It is nothing but linear inverted pendulum model. We are very much well versed with pendulums and inverted pendulum from school days onwards, right? So I could see that if I can control my LIPM using any of the strategy, any of the existing control strategy, and ensure that it is not falling, that mass is not falling, then I'll be able to control my humanoid lower portion for my gate plan. Okay. So that is what we have done in that paper. What we have done, again, when we go ahead with the inverted pendulum, the only variable component which we are giving over there is nothing but the height. That is Z. Okay. And that means, if I consider the heat portion of that from ground, how far or, how much distance mean that point is actually located for that center of mass concept. Okay. So if I can identify if that Z is variable, we can see that the heat portion will be actually, even moving little bit up and down with reference to the gate, right? So that would be the one variable if I consider the inverted pendulum. And inverted pendulum modeling is very easy, right? It is actually, if I go ahead with MGL sin theta, I'll be able to, that is what is the dynamic equation which is associated with your LIPM, right? So, if I, but at the same time, if I go ahead with the humanoid dynamic equation, I need to go ahead with the closed loop dynamics, I need to go ahead with the open loop dynamics, either I need to go ahead with the Newton-Euler formulation or you need to go ahead with the, the Lagrangian methods or combinations, or that means, Newton-Euler kind of methods, which is going to be very, complex and, it is going to become difficult. We need to analyze the closed loop, open loop. Okay, when you lift the leg, the mechanism will be open loop. When both the legs are in the ground, it is nothing but the closed loop, right? So the dynamics will be different for both the cases, and according to the changing gate, okay, we need to change. We need to switch between these two models, right? So that also we have done. But for this particular simulation, we have used the LIPM model. Once we identify the LIPM model, what we have done is like similar to the the research we have done in the 2 and 2.5D path planning. We have considered a plane. Okay, that plane is nothing but x, y, z axis is actually we have fixed, we have constrained. So this is going to be a BIBO system. Okay, bounded input, bounded output. Okay, we are saying that the height, the z-axis height of this two-leg mechanism is not going to go above this limit, and it is not going to go below this particular limit also. Okay, and so we have desired a platform. We have fixed the level, a plane over there, and and the z component we have fixed. That is where you find the first equation in that particular paper. And after that, what we have done is nothing but the LIPM dynamic model which we have identified, we have put it in a state space format and we have analyzed using, the basic controller methods. Okay. Then, UDE, that is nothing but, what is the UDE? Uncertainty and disturbance estimator method. Okay. So similarly, we have different methods to basically analyze this gate planning. It can be basically capture point based, or ZMB, zero moment point based, or it can be different control methods based like UD and combinations of all this kind of controllers also. Okay. So coming into this, after defining that plane, we have written that equations in a state space model. We have analyzed that and identified the output, it was not stable. Then, we try to, include the uncertainty component and estimated disturbance along with another controller. Okay, that is nothing, simple feedback controller we know. State estimation, right? State estimation feedback controller. Each and every state from the feedback it will be estimating and it will be basically giving to the controller input, right? So after estimating it, it will correct the control output. So that state feedback control along with your UDE, when we combined it, it was basically giving us a better performance. Okay. So that is where you can see all the equations in that paper. Okay. How it is actually getting modified and deviated and things like that, and how we are actually estimating and correcting that error. And when we use this combined controller, basically it is giving a better performance than a simple controller which we have previously used. Using the inverse, pendulum method, linear pendulum method. If you use this particular, the second output, which Lysinas was like, we have model using LIPM. Now, if I use the same controller in my actual robot, okay, that means we have different type of, humanoids which is starting from now onwards. Now, humanoid robot which is actually very small, right? So, if we implement that, whether it is going to function or not, then we have implemented, we have in our robot in lab. So we have implemented and we have ensured that it is giving you the same response as we have simulated, and it is following the gate basically. It is actually moving in a straight line path. Okay. So that is going as the second paper. It is already under review. Like that. Okay. So this is what is actually given in that paper. Now what is the LO associated with this? Learning objective. Okay, each one of you can identify your LO and we can discuss. Yeah, but initially we cannot say that we will use UDA only. It can be anything. We can say that we want to design a stabilized gate planning for two-leg robot.
How to define the governing
Governing equation from dynamics point of view or control point of view? Control point of view, you know that, we have, there are different approaches again when we talk about control problem. You can go ahead with model-based controller or model-free controller. If you are going ahead with a model-based controller, you will have all the parameters which is associated with the system in your hand, right? So you can go ahead with the inverse dynamic control problem by using with the help of the known parameters. That would be one ideal way of doing it. And if you have if you don't have your you don't have to go ahead with the model existing model. So there are some changes coming into picture. That's what we have discussed in the morning, right? If there is any change comes, the model based controllers will basically fail in controlling it. So that is where we can go ahead with a model predictive controller, okay, where it will predict the system parameters with reference to the existing parameters, okay. So you will be able to control with reference to that also. Otherwise, you have some intelligent kind of controllers, learning based controllers, okay, which will automatically estimate the parameters and it will contribute towards the controlling of that particular system. Yeah, ma'am. There is nowhere we can go ahead with the open loop system control over here in robotics. Whichever the control method we are talking about, everything should be for closed loop only. Without feedback, you won't be able to do anything. So the referencing parameters and all is given actually which trajectory I want to follow and whether the desired model is actually following the trajectory or not following the trajectory. If it is, there is some delta difference that is also given. The first control method actually have giving me some, steady state error, right? It is giving some steady state error. When I combine UD with SFC, it is giving me better performance. It is exactly following the trajectory, right? So you can write your LOs and all. Only LO, sir, only LO they need to submit, right? Learning objective from paper point of view. Yeah. You can prepare your LO and you can send it to me. Okay. We will have a look at it. Do you have any doubt or clarification in the session? Yeah, that's what that has gone as a second paper in Automatica. It's under review. So whatever the control method we have proposed, the same UDE based SFC, we have implemented in Navo robot. Okay, so here it is an approximate model which we have followed using LIPM. There we have used first exact model. That means exact 16 degree of freedom model we have used in simulation. We have identified the results. Then we have given the same control to the same UD and SFC controller to the Navo robot through the controller which is inbuilt in Navo, and it is actually following the given path planning, motion planning it is possible to do.
What are the computational requirements?
Okay, it actually basically depending upon the platform. If you talk about a humanoid, you will be able to find a 6 degree of humanoid also, and you will be able to find somewhat around 50 degree of freedom humanoid also. If you see a simple palm, when we talk about humanoid, the major contribution will be from hand, right, to do some job. If you consider that the palm, the human hand palm, this we call it as gripper in robot, right? How many degree of freedom it has? Only this much portion. How much? How many degrees? 3 degree. This is the least one I heard. How many degree a single finger has?
8 degree.
6 degree in single finger, sir? 3 degree in single finger? Yeah. It depends on your consideration. It can be minimum 3 or maximum 4 generally we consider. So whichever the research paper if you take it related to the palm control, you will be able to find 15 degree to 27 degree minimum. Okay. Depending upon the considerations and constraints. Single finger if you take it, there are minimum 3 revolute joints are here. You can see here that the first portion you will be able to bend it over here, right? Second you will be able to bend it like this, and third you will be able to bend it like this. Then you will be able to move like this, right? A sliding motion, right? So basically 4 degree if I consider in a single finger, for 4 fingers it will be 16, right? Then we have thumb. So 1 degree, 2 degree, again 3 degree, right? 16 plus 3 is 19. Then if you can see the connections over here, this is actually bringing some restrictions into your motion, right? So altogether, if you consider minimum 21, it will be basically there. Okay. Now, I'm sorry. So now, if you consider 21 degree of freedom, how do you control this 21 degree of freedom? Isn't it very easy for you to control? No. So that is where the miniaturization is actually, or scaling down is coming into picture. We will restrict few motions, okay, with some condition, and we will be actually moving the fingers. For example, if you want to grip something, okay, and we have different type of grips. That means you have spherical grasp, we have cylindrical grasp, we have pinch grasp. Okay, there are different kind of grasp which we have if we want to pick up some object, right? So that grasp and this degree of freedom movement very closely associated basically. Okay. So if you want to grip some glass, you need to ensure that all the four fingers are in one side and it is bended in this way, and the thumb is in this direction. You will be able to go ahead with the cylindrical grasp. If you want to pick a ball, you will preferably use a spherical grasp. You will be going like this and you will be grasping it. Sometimes to pick a pen, right? To pick a pen, you won't use spherical kind of grasp or cylindrical kind of grasp, right? You will go ahead with this pinch kind of grasp, okay, which is something like that sort of pinching, okay. So in and about 500 type of grasp is actually available. I mean in place. For each and everything, the coordination and movement of the fingers are actually very essential. You should have a very good clarity on that. Similar way, if you have a bipod mechanism, you want to navigate each and every joint movement it actually plays a role. Okay. If there is any constraints or restriction coming into picture means you won't be able to follow that particular path. That is where your support vector polygon is actually playing a major role. Anything else?
Can be controlled by argument.
Oh, yes, it depending upon the complexity which you have. If you have, if you are planning for an online path planning using camera images and all, then Arduino won't be sufficient. Okay. Raspberry Pi will do the minimum justice. You can have a Raspberry Pi camera inbuilt in that. And you can do, I think 20 frames per second or something, or 12 frames per second you will be getting from that camera. That will be sufficient to process. That will be able to process by your Raspberry Pi, and you can go ahead with that.
I just want to do most of it on pattern.
Okay, most of it.
So it is possible with the argument. Because
Yeah, it is possible. You can do it. But how do you identify the obstacle?
you can play the
Plain surface. Okay, predefined area, indoor kind of environment where is nothing is there. Okay. You should have at least some bump sensors, like suppose if the terrain is irregular. Okay, it should again there are so many parameters actually in that. The cutting height, the blade size, then it should not hit any wall or any pipe or something like that. So all those things you should have minimal amount of sensors in that system too.
data sharp. Simulation.
You can start with an existing system, maybe Turtlebot, or you can start with, there are so many inbuilt robots available. You can try implementing your algorithm into that and see that if it is functioning properly. If it is functioning properly, there is no issue. Otherwise, you can correct that algorithm. Then ensure that it is working. Then you can put it into your model.
Compared to humanoid robot.
Hmm.
So fly robot, if we do the path planning, so with respect to kinematic control,
Mm.
it is easier in
Yeah. So when we talk about this many degree of freedom for navigating in the ground, that means ground when we consider it, we are bothered only about the X, Y component. Even if we talk about the humanoid control in for the gate, the height is actually bounded. We don't have any issue, right? Bounded input, bounded output, that height problem. Okay. But coming into your aerial vehicles, okay, again we can classify them into three category. That is nothing but rotary wings, fixed wing, and flapping wing. Okay. So all three, the actuation methods are actually different. With reference to that, the control problem complexity is also different. If it is a rotor based, you will have propellers, 4 or 6, depending upon the chassis weight and all. You need to create that much thrust to lift, basically. Okay. Flapping wing means you need to ensure that the wings are actually getting flapped with reference to the movement. And sometimes it will be, you would have seen this birds, right? Few birds. It will after some time, it will be actually keeping the wing very flat like this for the moment. So all those techniques you need to understand before implementing that or simulating that. Each and every movement is different. For example, as we were discussing about the humanoid. Have you ever analyzed a quadruped movement? Because means an animal which is having 4 legs. For example, dogs. Dogs also has 4 legs, right? How it moves basically? Again, we can classify the movements or gaits. Okay, how it is like when it is silent and it doesn't have to move with so much fastness. One by one, it will move his leg or hand. Okay, then it will be reaching the position. At the same time, it identifies something and it need to, reach that fast. It will run. How it runs is nothing but two front hands will be working together and two legs will be working together. Okay. It will jump kind of, it will run like that. Okay. So depending upon the situation, even they change the pattern of gait. Okay. So it is like that. That I will share in the group. You just let me know which all you are interested in. All those we will share. I mean, you will be able to find some lecture series from Osmania University or something like that, so one of the foreign university. Few lectures are available. Apart from that, you can find some edX courses. edX courses you can identify. Then, if you know this Lyndon Joseph, he is one of the well-known in India. Uh, Robotics or something like that is his company, if I'm right, if I'm not wrong. Cochin, he is located in Cochin. He authored in about 6 to 7 books in ROS. From ROS 1 onwards, he has series of books.
The simulators,
Hmm.
can we download the code to the real hardware?
Yes, sir. Actually, Webot also has one. You know that MATLAB can directly download the code into any controller. ROS also has the same capability. You will be able to. Initially, we used to do something called as ROS Arduino bridge or ROS Raspberry Pi bridge like that. Nowadays, even that is not required. If you install ROS kind of platform, you have the facility to install ROS kind of platform in Raspberry Pi or NVIDIA kind of platform. So it is, it is like a mini CPU you have. Like how you have your computer, similar way your Raspberry Pi or NVIDIA will work. It is a mini computer where you can actually start writing the program itself, you can start from there only. That is what is one of the advantage of these platforms. Anything else? Okay. Thank you.
Thank you, ma'am. Thank you for the informative session. Now I would request Professor Prachi Rao from St. Francis College of Engineering, Mumbai, as well as Professor Sushma from Puri Institute of Technology to do the honors.
नहीं, पूरा सर आप थैंक यू मैम, थैंक यू फॉर योर
Come with all participants. All participants.